Yo. Okay. No, I'm going to do all AB, and then because there's an overlap. So I'll do all AB, and then one BCFRQ at the end on series. But really, by seeing the AB, the BC kids will be just fine. So, oh yeah, I'll give it a couple more minutes though. No, you had all week to watch me do the N3 homework. I don't care. I don't need other people. I just care about my students. I don't want. I don't really care if other people see it or not. True. I don't think you can add calculus. It's not really designed for that. How many ads? I'm not even running ads. That's so funny. I don't understand how the ads work. I apologize about that, but you know. Just enjoy the ads. Mic is so crisp. Good. It's better than my other mic. That's because I'm using a headset here. This is optional. You don't have to watch this. All right, I'll probably give it like 3 more minutes. But the goal is I have them already picked out, so this will go fast. I already have all 7 FRQs I want to do. Some of them we've done before. But I think they are a good collection of what I expect to be on the AP test. And I can't check who's on the stream. So yeah, we'll bounce from one to the next. And I'm not really going to wait for you to do them on your own. You're more just kind of going to, it's like a cram session. You're just going to watch me do each one. Some of them I'll go all the way through, depending on how long they're taking. I might just kind of like show you the setup and then move along. I have my calculator, but sometimes it's really slow to type this in. So I might just jump to the next one. And then I'll mention other things that could pop up on these types of FRQs. But I've picked the 2 that I think you're going to see on calculator and the 4 I think you're going to see on non-calculator. And then instead of a grab bag, we're going to do graphical analysis. I think you'll either see a graphical analysis or a table analysis. One of those 2, for sure. But yeah, I know. I was thinking about if anyone's obnoxious, I should have a moderator that would kick him out, but I don't think that's going to happen because I didn't open this up to a lot of people. So you do not need to know about cylindrical shells method. They took that off the AP curriculum a while back. It is pretty cool, but no, it is not contained in our content. All right, 1 more minute and then I'll start. I should teach summation. No, you should watch it's not hard. And then we'll talk about it in N3 tomorrow. Summation's pretty basic. I know you would, Joe. I think related rates will be on it, and I have it in one of these problems. I'm not going to do the proof of Euler's formula. That comes in BC, and I already did it in one of the BC classes, and I don't think I did it with the other one, which is kind of funny. All right, let's start, and I'm going to just give you a quick breakdown. Okay, so here we go. Sad banana. Yes, I know I should have the sad banana here. That's so funny. Okay, so AP test is tomorrow, obviously. You need to be there at 7:30 a.m. I will probably be in my classroom around 7:30 a.m. If you do something stupid like forget your calculator or something, I'll have a few extra to borrow, but you should charge them tonight, and you should have extra batteries on hand. I have some also. So if you do something bad, come by and see me if you need something. But you need to go to the gym. It's the new gym. All the AB and the BC kids will be in there together. I think BC will be in the back of the room. AB in the front. Yep. So the overview looks like this. You have an hour to do the 30 multiple choice non-calculator. Remember, they are all worth the same and there's no guessing penalty. So spend the time on the ones you know how to do. Don't stress the ones you don't know how to do. Sometimes there are tricky ones. You can go back and work on the ones that you skip, but you should go through and find the ones you have seen before for sure. We've been doing practice in class. Find the ones you know how to do. Your basic derivatives, your basic antiderivatives, some of those more basic graphical analysis, implicit differentiation, increasing, decreasing, concavity, all of that type of stuff. Do those ones. Some of your basic limits, maybe a L'Hopital's rule. Like, look for the things you know how to do. If there's one you don't know, move along. Okay. At the very end, you should guess. You always need to. You can always put an answer for everything. Sorry, I'm not going to read too much of this chat because I gotta. Yes, you can chart. No, the chart calculators I gave you are battery. So if it's out of battery, I'll have a couple AAAs. I need to give them to a proctor tomorrow so we can have them on hand. Okay, after that, you have 15 calculator multiple choice. These ones are usually typically easier. Now, the one thing, we didn't do a lot of these ones because I focused more on the non-calculator. The thing to be aware of here, you're mostly going to use your calculator to solve equations that you should not try to solve by hand. So if you get down to the problem and you have to solve an equation that's some crazy thing like natural log of x squared minus 7 plus cosine x or something ridiculous equals 3, and you have to solve this equation, you should never, ever, ever solve an equation by hand when you have a calculator. And I've tried to show you this all year, but people tend to forget. Remember, all you need to do is get everything to one side so that it equals 0, and then graph it and find the root. That's what you need to do. You graph it and you find the root, and usually it'll be in some interval that you're looking at. So don't solve equations by hand, just like you don't take derivatives by hand. Don't take or definite integrals by hand when you have a calculator. Remember, your calculator can do math 8, math 9, solve equations. It can find roots. It can find intersection points. So remember, if you have your calculator, think about all the things your calculator can do. Yes, we'll get back to that I'll talk about that real quick when we get there, the coefficients. Anyway, all right, and then there are 6 FRQs. So now, can we go back and do the non-calc MCQs during the calc? No, because you'll have your calculator. So once these are done, but that is true here. So you'll get to do the 2 FRQ calculator ones for 30 minutes. And then once you're done with that, you put your calculator away, but you have access to all 6. So if you need to go back and fix up some of your writing, you can go back and do the 2 calculator ones after you have the 30 minutes, but you have to put your calculator away. And then you have an hour for the 4 non-calculator FRQs. Now, remember, you're not trying to get a 9 out of every single one. You're trying to get as many points as possible. Do not draw pictures. Do not leave anything blank. Even if you don't know the right answer and it asks for units, give an answer and then put units. If you think your answer is totally wrong, but you need it in another part, give an answer and then use it in the next part. So don't write nothing. You get a lot of points for showing work. You get a lot of points for units. You get a lot of points for those little things. So you should never leave anything blank. Don't put a bunch of stupid stuff, but be smart about what you put. You also, if you put something incorrect, they will mark you wrong. So remember, don't ever say it. Don't ever say the function. You need to say the derivative. f of x, g of x, g prime of x. You need to talk about what function you are talking about. Never say it in the FRQs. All right, and with that, let's actually just get into some of these so we can start refreshing our memory on how these work. So I have 6 that I think, based on what's been on the last few years, I think could be reasonable for the 6 FRQs you'd expect to see. That's an interesting thought. Okay, so the first one is calculator. And I have these in the order you'd probably see them on the AP test. Check it out. People enter a line for an escalator at a rate modeled by the function r. So they are giving you a rate function. They tell you it's a rate, and then they say the units is people per second. So in other words, we have the people enter a line, and then as people get on the escalator, they exit the line at this rate. So this looks like an in-out accumulation. So this one is our in-out. I have not seen an in-out. I think the last 2 years we haven't seen in-out accumulation. So you can expect an in-out, I would believe, this year, I think. Now, remember, sometimes I was talking about there could be 2 in rates, and the problem is similar. Just if you have a rate, you're going to be accumulating it. So just pay attention. This is a rate in, and it's actually a piecewise function because it involves 2 pieces. You have this part for when we are between 0 and 300 in terms of time, and then this part, the rate goes to 0 for bigger than 300. So people stop getting in line after t is 300. And then you have your out rate. Now, this is something I think you could see this year too. Notice the out rate is a number. Well, what on earth does that mean? It's just a function. So just pretend like this is your out rate, and it doesn't matter that it's constant. It's still just a function. So it's still an out rate. It's a function. We're going to treat it just like the in rate function. It doesn't have a name. If you really wanted to, you could call it O of t for out and just say it's equal to 0.7. Yeah, probably. These are a while back. I don't know which one this was. And then look, there are 20 people in the line at t equals 0. That's our initial condition. So remember, always read everything, because if there's anything in there that they tell you that doesn't seem like, why are they telling me this, it's probably important. And in this case, they didn't say anything about concavity. They didn't say anything about increasing, decreasing, none of that. So chances are that there's nothing else there that I'm going to need. So in part A, how many people enter the line? Just enter. Not the total number of people in the line, just how many people entered the line for the escalator during the time interval from 0 to 300. So literally all you're doing is accumulating from 0 to 300. Usually part A of something like this is a basic accumulation just to kind of get you on the board. So I would always show my work. I don't care if you're like, well, I already know I'm doing that, just give the answer. No, you should write it out, so that if you make a dumb mistake in your calculation, you still get credit, okay? And then remember, we store it here. Make sure you are very careful about how you store this in your calculator. To the third. I'm going to do this maybe once or twice. I'm not going to do this for every problem because this is going to take forever plugging them in. But use your parentheses. Be very careful. If you're not quite sure, you can always overuse parentheses. If you're dividing by just one number, you don't need parentheses for the denominator. If you're dividing by something like 300 pi, make sure you put the denominator in parentheses. And then this is to the 7th power. Okay, so that looks good. 1 minus, or you could put this in parentheses if you're scared, but this should be fine. So then we do math 9. Mine looks like this, as most of yours do. If you have the other notation, that's on you to figure out. And then variables. Y variables, function y1, we've called up our function. And these problems should be rooted in reality. In other words, how many people enter the line during 0 to 300 if there's 20 people in line to start? It makes sense that 270 is a reasonable answer. To 270, pay attention if they say to round to the nearest person. In this case, it was a whole number, but you don't need to round because it was a whole number. They did not ask for units. How many people enter the line? So either don't give units, or if you're really confident, you can give units. But if they don't ask for units and you put people per hour, you're going to be wrong. So don't ever give more information than you need. All right, the next part. During the time interval, there are always people in that line for the escalator. How many people are in line at time 300? This is where I like to do the thing where I create the total function. So how many people are in the line at time 300? So I always do let t of t equal total people, or you could just say total. That means if we have a candidates test down the road or other things, we can call up a total function and talk about the total number at any time we want. So I like to do this. I don't know if Mr. Yip does this in his class. I don't think he does. It took me a few years to kind of get to this notation, but I like creating the total function, and I'm trying to find the total at time 300. So in this case, it's going to be initial condition, which is your t of 0, plus your accumulation in from 0 to 300 of your in rate, which is r of t, dt, minus your out rate from 0 to 300. Now, the problem with this one is people are confused because it's a constant function. Doesn't matter. It's still just a function. So you still have to accumulate it because it is a rate. If it says include units, you include units. Hold on, I'm looking at some chat. So do we round if it isn't a whole number on an FRQ that has people or something like that? Only if it says to round. So never round unless it explicitly says to round. Unless it explicitly says to round. I think if you're going to use a total function like I do, you should always define it. I don't know what they're looking for. They're probably just looking for this part, and then you just give the answer. But I like creating the total function because if I had to do a candidates test, I could then just say find where t of t equals 0, and then I could do the candidates test for like t of 0, t of 10, t of whatever I'm looking for. So I would define it if you remember to do that on the AP test. All right, and then you get your answer. Does this say one to round? How many people are in line at time 300? I'm not going to plug this whole one in, but we already found this first part. It was 270. So you would add that to 20, and then you would subtract whatever this value is, 0 to 300 of 0.7 dt, and that will give you the total number of people in line at 300. We've done lots of those. So if it's a rate function, I guarantee you're going to be accumulating somewhere to find a total if they're giving you a rate. If it's a single rate, you don't have to do in minus out. If it's two rates, in minus out, do in minus out. And if it's two in rates, then it would be plus and plus. Never seen two in rates, but I guess that could be a thing. Okay. This question is a little unique. So this is one that's kind of not a major one we have done before, but this is a cool problem. So far, usually that's a good question. How many on this FRQ? Probably 4, 2 and 2. Usually when there's 4 parts, it's like 2, 2, 3, 2, or 2, 2, 2, 3, or 2. So I imagine just think about 2 points per. Usually 1 for the setup, 1 for the answer. 1 for the setup, 1 for the answer. Yeah. For t is greater than 300, what is the first time that there are no people in line for the escalator? All right, so let's do this. I actually do need the previous part because this is a cool problem. And I bet they're going to do something like this somewhere because I haven't seen it since this escalator problem. And it's a good problem. And it's a good thing to go back and talk about. So actually, let's go back and let's accumulate and actually get the answer to the previous part. So math 9, 0 to 300. Stop that. 0 to 300. Oops. And then we'll plug in 0.7. Remember, even though it's a rate, we still accumulate it to get our total. 210. Okay, so these are whole numbers. They were nice to us. So in other words, in this part, we had 20 plus 270 is 290 minus 210 is 80, if I did that right. Check with your calculator. It'd be really stupid to make a bad mistake here. So there are 80 people in line. So at time 300, we have 80 people in line. Well, we're going to talk about C. I think you're getting ahead of me on C. Okay, so what is the first time that there are no people in line for the escalator? So in other words, I'm trying to find when t of t is equal to 0. And I'm trying to find the time where that happens. Well, in this case, we pay attention to the rate here. The rate was 0 after 300, so nobody's getting in line after 300. So this problem's really cool. You're basically saying, okay, I need to find the time where there's 0 people in line. So, I want to find the time where the total function equals 0. Except there's no more in rate, so I'm going to start at time 300 because that's when the new rate kicked in, where there is no more in rate and all we have is an out rate. And I'm going to subtract from 300 because that's the time I'm starting at because our initial condition is 300. And I'm going to go to some unknown time t that I'm trying to solve for. And I'm going to put my out rate here. And then don't use the same variable here. Remember, we use a dummy variable if t is our variable outside. And this is the setup. So this is a tricky question for sure. This year would probably be worth 2 or 3 points, and I bet people would miss this point because it's a weird setup. But the point is, you know, at time 300, there were 80 people. Now, what do we do here? You can't do an integral like this, an accumulation function, when it's got a bound. Your calculator won't do it, but that's why they gave you such a basic function, because you can take the antiderivative of that. The antiderivative of 0.7 is just 0.7x evaluated from 300 to t. And then that equals 0, or we want to find when it equals 0. So then you just plug in top bound minus bottom bound. So it'd be 0.7t. Make sure you put in parentheses minus 0.7 times 300. And then you solve for t. Now this is one that's not terrible. You can you don't have to use your calculator to graph it and all that stuff, but you could. So you have an equation, you have a calculator. Let's distribute that negative. 0.7 times 300. Oops. 0.7 times 300. 210. So subtract the 210 over. Add the 80. So subtract the 8. So it'd be 290. So 290 equals, actually it's a negative 290, equals negative 0.7t, and then solve for t. So 290 divided by 0.7, 414. And I don't know if it asked me to round. Remember, 5 decimal places. Now that may be different for Mr. Yip. It is 3 when you're done with the problem. So you could technically, since we're done with the problem, round to 285 or 285 or 286. I'm a fan of just always keeping 5, because the grader will cut you off and you'll get the right point. So even though this one does round up to 2.286, the grader will see this, cut this off, and give you credit for 285 or 286. So this is a cool problem. We haven't done a lot like this where you have to solve for the bound, but that's why they gave you such a nice inside function here. So you could find the antiderivative by hand, plug in your bounds, and then solve for the bound. Is that going to be on your AP test? I have no idea, but it's a cool problem. And then part D, they get right back to the last important thing, which I really want to make sure we remember. They say, for 0 to 300, at what time t is the number of people in line? Ding, 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 a minimum, aka candidates. Candidates. Call back to when we didn't know how to spell it. Make sure you spell it right. Candidates, but I don't think they'll mark you wrong for spelling, but don't be obnoxious unless you know you're killing it. To the nearest whole number, find the number of people in line at this time. All right, so I might not do the accumulation part, but let's walk through our candidates test. Candidates testing. This is where you have to find the candidates. You get 2 for free. They are the endpoints. And now we can talk about them as our totals. It's the total at time 0. It's the total at time 300. Those are your endpoints. And then we need to find the internal critical point. And how do we do that? Well, to do that, you do your in rate minus your out rate. So I like to do it like this. I like to create the in function, create the out function, and then in y3, do my variables, y variables, function y1, minus variables, y variables, function y2. There's your in minus your out. Unselect the other 2, and all we're going to do after we change our window to be our interval, so 0 to 300, let's zoom way in. This is good enough, negative 2.5 to 2.5. We graph it. And wherever it crosses, there's 1. That's our first candidate. There's another one. And that's it. That's it. So how do you calculate your candidates, aka your roots? Well, let's back up. This one has to be a relative min because the derivative went from below to above. So this is going to be a minimum. I think this problem was asking for maximum. So that's not going to be the answer, but always include them in your candidates test anyway. And then here's the maximum, a relative maximum. So we second calculate the 0, and remember, go to the left of it. So you go to the left, enter, go to the right, enter a third time, bam, 33.013. So that's where I don't want you to round. You need to keep it to 5 decimal places, even 6 if you're really feeling adventurous. And then you accumulate to get that value, just like we did up here. So back here, you know how we got t of 300? You would accumulate. We already got 300. It was 80. You'd accumulate. Instead of 300, you'd plug in this value for all of them. And then you still have one more that I'm not going to spend time doing because I want to get to all these FRQs, and it's going to take me a bit. But that's the gist of this one. Definitely candidates testing is going to pop up here, or it's going to pop up in your graphical accumulation. So remember how to do it. It's your endpoints and your roots of the derivative, aka the critical points of the original. All right. Sorry, let me go back and look at how do you find the derivatives? Okay, that's spam. Classic. Okay, great. Okay, cool stuff. All right. The next one I think you're going to expect to see, because I haven't seen it in a couple of, I think the last time I saw it was 2 years ago. You're going to see motion. You're either going to see it as a calculator or as a non-calculator. Or you could not see it. I don't know. But I'm trying to hit you with all the ones I think you're going to see. And I think you're going to see motion. So this is a motion calculator FRQ. So with things with motion, remember, they're going to start you with the velocity probably and ask you to find things like position, displacement, total distance, speeding up, slowing down, moving forwards, moving backwards. When does the particle come to a stop? Things like that. So let's see what this one asks me. So remember, read everything. Particle P is moving along the x-axis, so it's one-dimensional. The velocity is given by, there's my velocity, for only from 0 to pi. At time 0, the particle is at position 5. So there's my initial condition. Cool. Oh, a second particle Q also moves along the x-axis. The velocity of particle Q is given by this fun function, 1.25 to the power of t. This is at times, for also 0 to pi. And then they give you its position. Okay, so this is just kind of obnoxious. There's two functions we're working with. One is particle P, one is particle Q. Find the positions of particle P and Q at t equals 1. All right, I don't know if I'll do both of those, but let's remind ourselves how to find the position. Now watch, here's the notation. Let's do P first. Position of particle P at time 1 is equal to initial condition plus accumulation. So the velocity of P at time, whatever they give me, which it looks like time 0. Oops, that should not be a P. That should be a P or a big P. So the position of particle P at time 0 plus the accumulation from where you're at 0 to where you're trying to get 1 of the velocity of particle P. And you plug all of that into your calculator. It would be 5 plus, and then this accumulation that, again, don't do it by hand if you have a calculator. So I will do this one. And we're going to plug it in. So sine x to the 1.5. Now, at this point, as soon as I see a trig function, you should definitely make sure that you are in radians and not degrees. I found out last year that even if you're in degrees, there's a separate answer key and you can still get credit, but don't be in radians. That way you don't make the grader mad at you. So don't fear though, if you freak out because you forgot to put it in radians, there's workarounds for that. Although the multiple choice, I don't know, that's a different question. So be in radians. Which one? All right, let's accumulate. So second quit, math 9, 0 to 1. Call up your variables. Y variables, function y1, dx, bam. 0.37066. Add them together. That's your answer. 7066. And do they ask for units? Find the positions? Nope, this doesn't even give units. So that's it. That's our position at time 1. You do the same thing for Q. I'm not going to do it for Q, but it's the same idea. Plug it in, initial condition plus accumulation. Now, part B is a cool question. But we're not going to be able to do it if we don't do the other position. So we'll just talk about it. Are particles P and Q moving toward each other or away from each other at t equals 1? So in other words, you need to find 4 things. You need the position of P at time 1. You need the velocity of P at time 1. You would need to find the position of Q at time 1. And you would need to find the velocity of Q at time 1. I would always put 5 decimals just because At the end, it's fine if you round to 3. But I'm saying if you ever use, like in this last problem where we had our bound, you'd never want to round here, because if you round here, it's going to throw your answer off at the end by too much. All right, so in this last problem, I want to remind you of something else, which is why I chose it. I may not go through the entire thing, but remember how to do this. If I give you the velocity function, there it is. Don't ever plug in by hand. Instead, do this. Go to second, table set, and tell it to ask you for values. And then go to your table and plug in 1. And that gives you the velocity, which is positive 0.84147. Remember, the table will give you values, so you don't have to sit there and plug things in. And yeah, you don't have to simplify any of these values. Yeah, that is a good point, but we're not going to. Yes. All right, so at this point, particle P is moving forward. That's what a positive velocity means, so forward. Which means, let's say he was at 5 and he's moving here. I think the way this problem worked, I'm going to just really shorthand this. Let's say particle Q was at position 8 and it had a negative velocity. Well, that's the work you would need to show that says they're moving towards each other. I don't know if that's true. It's definitely not 8, and I don't know if it's negative. But the point is, to find positions you accumulate, to find velocities, you just straight plug in. And in this case, if you want to see if the particles are moving towards each other, their positions matter. So you have to know where they're located and in which direction. Positive velocity means moving forward. Negative velocity means moving backwards. Okay? So in this case, the way my hypothetical situation, I said that the particles are moving towards each other. And that work is all you need to show. Okay, find the acceleration of Q. Is the speed of particle Q increasing or decreasing at t equals 1? I'm going to change this because I've already done the work for P. Let's just talk about P. All right, so speeding up, slowing down. That's something we've done tons. So the velocity of particle P at time 1 is 0.84147, which is a positive value. To find the acceleration, don't do it by hand. Math 8. And then you already have your function stored as your velocity. So variables, y variables, function y1, d, and then at 1, and we get 0.81. Okay, I thought it was the same value for a second. So the acceleration at time 1 for particle P is 0.81045, which is positive. And since both of these are positive, we would say speeding up. You don't have to say in the forward direction, but you say the speed is increasing or speeding up. Speeding up because both of these are positive. Now, be very careful. If they ask, is the velocity increasing or decreasing, you don't look at the velocity. All you look at is acceleration. So if I ask you, is the velocity increasing or decreasing, you just look at the acceleration. And if acceleration is positive, your velocity is increasing. If acceleration is negative, velocity is decreasing. But if they ask for speed increasing or decreasing, then you need to find both of these signs. And if they're both the same sign, you're speeding up. If they're opposite signs, they're slowing down. Yeah, well, it's too late now. Okay, so yeah, that's going to come up. And then find the total distance traveled. This is just a good reminder. I'm not going to type this one in. To find total distance, you accumulate from 0 to pi. Absolute value goes inside of the integral. Plug it in, get your answer, and that's it. It's probably 2 points. Show your setup and show your answer. It might just be 1 point. I don't know. But this is a good motion FRQ. This is the type of stuff you'll be asked. Sometimes they might ask displacement. At that point, you don't have absolute value. But in this case, total distance needs absolute value. Okay, I can't help you with that stuff, okay? All right. Next one. Now we're done with the calculator stuff, so let's put this away. Now we're going to move on to, let me scoot these over. I think your non-calculator ones, last year there was a really abstract area volume. So I think you're going to have a more nice area volume this year. A little more. Okay, anyway. I think this is going to be what we're after. So this is a good one to go through. This one's pretty basic, but definitely something worth talking about that will also get us into something good that we can review. So here is an area volume FRQ. How do you know it's area volume? Well, because they say things like find the area, find the volume. All right, so question A, let's make sure we don't miss anything. Let R be the region enclosed by the graphs of, they gave me g of x and h of x. Which is which? Cosine probably is this one that's going back and forth. So I might draw to myself that this is g, and then this one is h. If you don't know, look, you can plug in 0 to both of them. If I plug 0 into this one, I get negative, cosine of 0 is 1, so negative 2 plus 3 is 1, so yes, this is g. Plug 0 into this one, I bet you're going to get 4, and you should. I don't know. It's a good question. I think you do it in pen or pencil. I don't know if they have you do it in pen. Actually, it might be pen now that I think, because I scan them in. I don't know. They'll have those for you, though. Pens, they'll have whatever you need, whatever writing utensil you need. Okay, so find the area of R. Please remember, area is literally top minus bottom, or right minus left. No squares, no pies. It is literally just start to finish. Now, if it's non-calculator, your endpoints are going to be nice. If it's calculator, you need to calculate the intersection points. So if it's calculator, graph them both, calculate the intersection point. But this is non-calculator, so you can pretty much guarantee it's going to be 0 to 2. And it says it is. It says x equals 2. And then I would just write it in so the grader knows you know what you're doing. H of x minus g of x dx. Probably get 1 point for that. But unfortunately, since this is non-calculator, you need to do it by hand. And yeah, that's why this FRQ is kind of gross. But it's just, we've done so many problems like this. You have to get over the fact that, oh, it's a lot of work. It's not that bad. You have to just go through it very carefully. And when you get to the very end, just Ellen method. You do not need to simplify anything. So stick it out, especially on one like this. I know it's a terrible setup, but you just go integral or antiderive piece by piece. You don't need to worry about the simplifying at the end. So here, let's see if we can do it. So the antiderivative of 6, 6x. This is a little baby chain rule. Raise it to a power, x minus 1 to the third. I want a 1/3, and I want that negative 2 to still be there, so negative 2/3. And there's nothing inside I have to worry about. Minus, we can distribute the negative now to do plus 2x. Minus, we'll worry about that sign in a second. Flip the cosine to a sine of pi over 2x. Derivative of sine is cosine, so I don't have to worry about the sign, so it really was negative because I want this sign to stay the same, and then this negative distributes here. And then I want the 3 in front to be there still, but I also need to cancel the pi over 2 because when you do the chain rule, you're going to have to multiply by pi over 2. So you need a 2 over pi in front. So in other words, you're going to end up with a 6 over pi in front. Evaluated from 0 to 2. Take your time here. These are a lot of little things we've done all year. It's been a while since we've had to do this many antiderivatives by hand because we've been doing calculator. But once you get that, then just one more step, plug everything in and move on. This is the bulk of this FRQ, is this part right here. So if you come across a antiderivative by hand, either here or in the differential equations, which we're going to do in a minute, just suck it up. So it's all that minus, I try to keep it on the same line, but I'm out of room, so I'm going to do it here. Plug in 0. That first term is 0. So this, use parentheses. You can even do 6 times 0 if you really want. Minus 2/3 times 0 minus 1 cubed plus 2 times 0 minus 6 over pi sine of 0. Done. Do not sit there and simplify this. Not even the trig. So this is an FRQ. They will give you credit for trig. Unsimplified. At least they did last year. So hopefully that remains. It should remain the same. You do not need to sit there and work this out. And I would not. Just a big old box. Okay. If you have one like that this year. No, because if you simplify and it's wrong, they're going to mark you wrong. And your call, but I wouldn't. Okay, that's the hardest part of this FRQ because it's just so tedious. Then this gets a little more interesting. It's a lot of setups. A lot of setups at this point. So, region R is the base of a solid. For the solid, base of a solid, and look, cross sections perpendicular to the x-axis. This is a cross-section problem. So top minus bottom, because it's perpendicular to the x-axis. So top minus bottom will give me my base length. So normally this is how it works. I called this the base length, which is top minus bottom. And then we had all of our area formulas. So the area formulas worked like this. You have your squares. Let's do this. Let's write them all out real fast just to remember. Yeah, I'm really busy. Yeah? Well, what? Question about the dog's medication. Okay, sorry. Top minus bottom. So usually when you're doing a square, it's just the accumulation of the base length squared. Top minus bottom squared, no coefficient. Right? Hilarious. Okay. If it's a isosceles right triangle, it's a 1/2 accumulation of the base length squared. If it's a semicircle, it is pi over 8 accumulation of the base length squared. If it's a rectangle with like height equal to 2, that's 2 accumulation of the base length. No squared, because the area is the height times the base length. And then lastly, if it's a rectangle with a height that's equal to 2 times the length of the base, which sometimes happens, then it would be 2 base length squared. Because the area, remember this is one I feel like I always have to draw. If this is the base length, the height is 2 times the base length. The area of this is 2 base length squared. Okay, so cool. That's fun. We have all these. I'm guessing it's going to be one of these. So it says cross sections that are, what is this? They did not give me a shape. They gave me an area, which is really weird. And you freak out because you're like, what is this even saying? This is the best case scenario because they're not giving you the shape. If they gave you the shape, we have to construct the area. If they give you the shape, you have to construct the area. In this case, they've given you the area. So all you need to do is accumulate that from the end or start to the end. So literally, it is just the accumulation from 0 to 2, no coefficient, of your area function, 1 over x plus 3, dx. Done. No squareds, nothing. If they give you the area, you just accumulate the area of these cross sections. That's it. So don't overthink these ones. This is what you want to see. If it's just a basic area like this, you just accumulate the area when you're dealing with cross sections. All right, and then at this point, take an antiderivative. Well, natural log of absolute value of x plus 3, and then evaluated from 0 to 2. Natural log of 5, you don't need the absolute value because it's positive, minus natural log of 3, and you're done. Because this one actually wanted the answer. No setup. Remember absolute value in logs. When you take the antiderivative involving a log, you need absolute values until you plug things in. Okay? So, looks worse than it is, but when they give you the area, it's actually really nice. All right, and then the last one, which we definitely need to talk about, let's find an integral that gives the volume of the solid generated when r is rotated about y equals 6. Y equals 6. Let's get rid of some of this stuff. No, we can keep it. Y equals 6 is up here. So this is where you need to take your time and go back through all of this. All of your stuff. All of the things I tried to teach you. I'm going to actually do the work up here so we can look at the picture. So right off the bat, horizontal line. Do I use x or y? We are doing horizontal, so x. So immediately set up your integral. 0 to 2 dx. Remember, if I'm viewing a vertical axis, you got to get everything in terms of y. But I'm doing horizontal, so everything in terms of x. Do you see blank space between the shaded area and where you are rotating? I definitely do. So immediately, 2 radii. Okay. we're rotating around not the x-axis, so we're going to have to add or subtract or something to these functions. So let's draw big R. Big R works as where you're rotating through the blank space to the outer edge. Bam. Now, what function does that go to? It goes to G. G is this distance between the curve and the x-axis. So we are talking about a bigger distance. And essentially what we want to do is take the whole distance, 6 minus G. So when you're rotating above, you do the rotation line minus the function value. If we were rotating below, that's when you add G plus. If you're rotating, well, those are only two I can really talk about in this problem. But if you're rotating way down here, you add. If you're rotating above it, it's where you're rotating minus the function. Okay, and then if you know that, remember the last thing, this is a free one because it's the same. It's never going to be different. So if it's 6 minus, it has to be 6 minus. If it's 2 plus, it has to be 2 plus. And this one, they just wanted the setup. They don't want the answer. All right, so that was a pretty straightforward area volume. They have not done a straightforward area volume in a few years, so I bet they're going to do this because the one last year was really wonky. It was the weirdest one in the AP test, I think. All right, next one. Let's scoot some of these guys over. Out of the way. How are we doing? 45 minutes and we've done 3. Okay. We also talked for a little bit. Cool. The next one. This was on last year's. I think it's a good FRQ. I don't know if you're going to see table accumulation this year. You'll either see table or graphical. Oh, Nathan, you're the man. Yes, I would have lost a point. How sad. Do not forget your pies. Sad banana. I almost forgot the pie. Anytime you're doing volume by rotation, nice. Anytime you do volume by rotation, you need to put a pi. So yes, very true. I would have lost that point, which is sad. It's a dumb point to miss. Volume by rotation, don't forget your pi. All right, thank you for the catch, Mr. Kwan. All right, this is a good one. So this was last year. I think Mr. Yip did all the ones from last year. You guys have never seen this one from me, but I like this problem a lot. This is a good one. Yeah, volume and area is in a singular FRQ for sure. All right, let's pay attention to this. Is a good one because I want to make sure we have all of the correct notation here. Oops. I'll kind of do it on the side so I can remember. All right, let's quickly look back and see at all the things. They're giving you a rate, it looks like. An ice sculpture melts in such a way that it can be modeled as a cone that maintains a conical shape as it decreases in size. Now, the thing about this one that I remember last year, that doesn't mean it has to stay proportional. It's just melting. So you could have your cone start out like this in all of its amazing glory. And then at the end, it could just be like this, where it still has a pretty wide base, but not a tall height. So it doesn't have to maintain proportionality. It's important for later. All right, and they're giving me the rate. The radius of the base of the cone is given by, oh, ding, 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 twice differentiable function. Why on earth are they telling me that here? Well, because they've given me a table of values, and I can't assume differentiability unless they state it's differentiable, which means I'm going to have to reply to that later probably. Where R of t is measured in centimeters and t is days. Okay, so R is the total function, and R prime is the rate. Great. Table above gives values from 0 to 12. Okay. Question A. Approximate R double prime of 8.5. Well, R double prime of 8.5 means the slope of R prime of 8.5. And they've given me R prime, so I just got to look and find the two values that are on the both sides of 8.5 and essentially just plug those in. So R prime of 10 minus R prime of 7 all over 10 minus 7 equals negative 3.8 plus 4.4 because it's minus negative. Don't make that bad mistake. All over 3. Show the computation lead to your answer and indicate units of measure. This is a rate of a rate. R of t is measured in centimeters per day. So it'd be centimeters per day squared. And you do not simplify this. Why? There's no reason. Just give them the answer. Just give them the answer. That's it. I didn't ask you to interpret it, but remember the way you'd interpret it, this value is going to end up being positive. So you'd say the rate at which the radius, or the rate of change of the radius is increasing because it's positive. You always have to use increasing or decreasing. So you wouldn't say the radius is increasing because this is the second derivative. You would say the rate of change of the radius is increasing at a rate of this, approximately at r double prime, or at t equals 8.5. Yes, you can write cm per day per day. And actually, yeah, that might not be. Sometimes I've seen FRQs where there was one that was like centimeters per centimeter and students simplified it. Don't do that. So if it's a weird unit, just leave the units. All right, it didn't ask me to interpret anything, did it? Nope. B. Is there a time from 0 to 3, for which r prime of t equals -6? Well, gosh. We went from, they're asking about r prime, and my table is r prime. So this is not a mean value theorem. This is an intermediate value theorem. To get from -6.1 to -5, I had to cross -6. So you have to be very careful about how you say this. So you would say, yes, answer the question. Since r prime of t is differentiable, it is continuous. You have to say that. If you're going to use the intermediate value theorem, even if you're going to use the mean value theorem, I would still say because the function is differentiable, it is continuous. That's the first condition. And since r prime of 0 equals -6.1, and r prime of 3 is equal to -5.0, r prime of t has to equal -6 in the interval 0 to 3 by the intermediate value theorem. Now, if you explain this and say, well, if I'm here and I have to get here, I have to cross here, you don't even need to reference the intermediate value theorem, it turns out. You don't even get points for that. You get points for kind of stating what the intermediate value theorem says. But I think this is a good answer. I think you should still reference the intermediate value theorem. You definitely have to explain yourself with those endpoints. So you have to say to get from here to get to here, you had to cross -6 in the interval. And you definitely want to say because the function is differentiable, it is continuous. Make sure you remember all that. That's like 2 points that you could miss out on for stupidity reasons. And then always make sure you answer the question, yes or no. All right, C. Use a right Riemann sum with 4 subintervals indicated in the table to approximate this value. Well, what on earth are we finding here? Remember, even if you're not quite sure what you're finding, this just literally equals r of 12 minus r of 0, aka the displacement of the radius, aka how much the radius changed. You're finding the amount. So if you get a value of this to be like 12, that means the radius increased by 12 centimeters or whatever the units were. Yeah, over the 12-day period or 12-hour. Yeah, 12-day period. But they didn't ask for that. All they want you to do is give a approximate value for it. But I just want to remind you what you're actually doing. You're accumulating a rate to get a total. In this case, it's a displacement. But I think because all of these are negative, you end up going to getting a negative answer, or shrinking, because the ice sculpture is getting smaller. So it makes sense. All right, and then I guess I'll do the work up. I'll do the work up here because I need to make sure I do this right. And for those of you that have Mr. Yip and not me, I don't know if you know this, you can leave this entirely unsimplified, and you should. So we're doing a right-hand Riemann sum. So right to left, and we're doing how many subintervals to do 0 to 12? 4. So 1, 2, 3, 4. So first thing, this distance is 2 times the height, which is -3.5, plus this distance, 3, times this height, which is -3.8, plus this distance, which is 4, times this height, which is -4.4, plus this distance, which is 3, times height, which is -5.0. And that's it. Don't sit there and simplify this. No reason. You're going to make a dumb mistake, and you're going to waste time. If they ask for units, they did not, but the units would be centimeters. But they didn't ask for units, so don't give it. That's it. That's going to get you 2 points. Don't simplify. You don't need to, and you're going to be wrong probably. You're going to make some stupid mistake. So that's it. I'm going to stop there. That was my part C. Good job, me. All right, and lastly, this is the related rates part. I'll come do it down here. So finally, the related rates portion, which yes, you'll see related rates somewhere. Anytime you have something changing as time changes, you're going to deal with related rates. So the height, do they give you the volume of a cone here? Oh, they do. Very nice. I think they have to. So right off the bat, we have our formula. If it's a triangle, use the Pythagorean theorem most of the time. Although on the FRQ or the HR MCQs, there was a tangent problem that was pretty gross. But here, they're giving you the volume. It'll probably either be a volume or it'll be a triangle. All right, so what's going on here? The height of the cone. So if you really want to spend your time doing this the way I showed you, which I don't think is a terrible idea, you have your function. You have your variables, v, r, h. You have dv dt, dr dt, dh dt. So let's identify which ones they're giving me in this problem. And some of them are probably hidden in the table, I bet. So the volume, the height of the cone decreases at a rate of 2. So -2. At time 3, the radius is 100. Okay. And the height is 50. Okay. That's cool. They didn't make me find either of those. Find the rate of change of the volume. So find this. Find the rate of change of the volume at day 3. Okay. So I don't think we're going to even need this. But dr dt we definitely need. And that's we have from the table. So dr dt at time 3 was -5. So this is actually a pretty straightforward one. I have everything I need. Nothing's really hidden. You just need to make sure you take the derivative correctly. And this is where I'm going to remind you to do the product rule. So this is a product rule situation. The derivative of v, dv dt. And then we have our two functions. We have 1/3 pi r squared. And we have our other function h. Please don't forget your derivative rules when taking derivatives like this. So it's derivative of the first. So 2/3 pi r dr dt times h times the original second plus derivative of the second, which is dh dt times original first, which is 1/3 pi r squared. Plug all of this in here and you're done. Don't simplify. Plug it all in. Don't simplify. Leave it. You're done. Do they want units? Find the rate of change of the volume of the cone with respect to time in cubic centimeters per day. Well, they're giving you the rate or the units, but yeah, not units on this one. But remember, you're finding the rate of change, so it needs to be a rate. So it's centimeters per day. And plug it in. I'm just going to stop early, but you definitely need to plug it in. All right. Cool. So that's a table accumulation. That was last year. I think you're going to see either, well, you always either see a table accumulation or a graphical accumulation. Last year, they happened to give both, which is really interesting. So I don't think that's going to be the case this year. Okay. Here's a problem we've done before. We've done this one, but I think it's a really good problem to go back to. Plus, based on what I've seen, I bet you have a differential equation word problem. You're going to have a differential equation somewhere, but I think it's going to be a word problem type. So we really need to go through this carefully. This is a good one too, because I think you can handle slope fields. I think you can handle solution curves. So this one doesn't have that. This one just has linear approximation, aka a tangent line, second derivative with overestimate, underestimate, which is very good to talk about, and then a separation of variables to find the particular solution. Yeah, we did this one. Okay, so yeah, we did it in class, which means you probably don't, I don't know if you guys have notes on it, but all right, so first things first, at t equals 0, boiled potatoes taken from a pot on a stove and left to cool in the kitchen. Cool. The internal temperature of the potato is 91 degrees, so that's our initial condition. And the internal temperature of the potato is greater than 27 degrees always. Okay, so that's actually pretty important. This potato, and I talked about this in class, this potato starts at 91 and basically, that's bad, basically starts to cool down, but never gets colder than 27. So it has kind of like an end behavior or an asymptote at 27. So pay attention to that idea that it's always going to be decreasing and staying positive. Concavity, which we'll talk about when we get down to it. The internal temperature of the potato can be modeled by the function h, and they give you the differential equation for h. And this is another reason why I wanted to give you this problem. Notice the differential equation. Students get really confused. This h is like y. It's not an x, it's the y. That's why this is a differential equation problem. If it was just x or t, it'd be a normal, ordinary derivative question. We could take the antiderivative like normal. But it's not t, it's h. So you need to remember that. Pay attention to what variables they're using. If this confuses you, you can do the strategy that some people do where they change h to y's and they change t to x. So if you'd rather say something like let t equal x and h equal y, you could do that and then just rewrite the problem and then go through it if that's going to confuse you. But if it's not going to confuse you, just remember that h is y. Okay, so in part A, actually I'll do it over here. We're going to make a tangent line. This should be very basic. Don't mess this part up. You need two things. You need an initial condition, which they give you, and you need the slope at the initial condition, which you get by plugging into the differential equation. And you're not plugging in 0, you're plugging in h, which is 91. 91 minus 27 is 64, and right, 64 divided by 4 is, was that 16? Yeah, so negative 16. If you're really scared about doing that, don't simplify it. You don't need to. So write an equation for the line tangent. Now let's write our tangent line. So in this case, since we're using h's, it'd be h minus 91 equals your slope, which is negative 16, times t minus 0. Add over the 91 because they want you to use this to do a linear approximation. And to do a linear approximation, you just plug in. They want you to approximate at time 3. So you created a tangent line at time 0 that does this based on the slope at 0. And let's say 3 was right here. You're approximating the temperature at time 3. So negative 16 times 3 plus 91. And does it want units? Use this equation to approximate the internal temperature. I mean, it would be degrees. And that's it. Makes sense that it's colder because it's cooled down. It's been sitting on the shelf or counter. And that's it. So linear approximation, use your slope. The slope is just the differential equation. All right, then we get to question B. Use the second derivative to determine whether your answer in A is overestimate or underestimate. Well, we can already tell based on the picture that I've drawn, this is going to rely on concavity, plus any time they ask you about the second derivative, you're going to use concavity. And this also plays when you're doing like the second derivative test. So remember the second derivative test? That's where you need to find the first derivative if it's 0, and then the second derivative is concavity, tells you if it's a relative max, well, sorry, relative min. If it's concave up, relative max, if it's concave down. That's not what this is asking. This just wants the second derivative. So let me remind you of another thing that you better not do. If this is your derivative or your differential equation, I'm going to distribute this coefficient so that I don't make dumb mistakes. So distribute it like this. And now take the second derivative. And why did I distribute it? Because I want to make sure you remember something very important. The second derivative is d squared h over dt squared. The derivative of negative 1/4 h with respect to time, or dt in the problem, is negative 1/4 times dh dt. Exactly. Plus 27/4, the derivative of that is 0. So in other words, our second derivative is negative 1/4, and then do not forget to plug dh dt back in. So negative 1/4 h plus 27/4. And then you could distribute, or don't, but the point is this. Remember, h always has to be bigger than 27. So if I plug a value for h in, like 90, 91, you're going to get negative 91/4 plus 27/4. This is always negative. And this is a negative term, and a negative times a negative is positive, which means the graph is always concave up, which I kind of drew to start the problem. And if it's concave up, that means you're going to, based on our picture, be under. Your approximation is under because the tangent line was linear. It thought that the motion was just straight because that's what a linear approximation does. But if the curve bends, which most curves do, if it's concave down, we'd be over. But since it's concave up, we have an under approximation. Cool. So yeah, remember our Riemann? We didn't do it in this last problem with the Riemann sum. Same thing here though. Remember, if it's strictly increasing, like in this last problem where we have the function, well, it was negative, it's a little weird. But remember how to draw the picture. If it's decreasing and you're doing a left hand, that's over. Oops, I'll show right here. If it's decreasing, it's a over. So just draw the picture if you can't remember all those little rules. That's what I like to do. All right, and then the last part, question C, switches it on us. Now they give us a new differential equation. And be careful, because sometimes they'll reference a particular solution. That's like, this represents a particular solution. Now do something. You don't find the particular solution unless they say find it. So like find an expression for g of t. That means find the particular solution. This is where all your points are going to come in. So we need to take our time here. And this is a obnoxious one, which is why I wanted to do it. So we have dg, where g is the y, over dt equals negative g minus 27 to the 2/3. All right, so remember, you never, ever, ever add or subtract in this step, ever. It is never adding or subtracting. It is always either divide or multiply. That's it. So there was sometimes, let's say this 2/3 wasn't here, people would be trying to subtract the g over. No, you can divide the whole term over and leave nothing on this side except for a 1. That is an option. Yes, Van Yam, you can do that. You can use it. I don't do it in my class because I always like to show the derivative or the variable, but you can use h primes if you want. Okay, so in this case, divide the entire term over. So you're dividing. I like to leave coefficients. So if this is a -2, a -1/3, a +1/3, I always keep the negative or the coefficient on the right. It just makes the problem easier. I'm going to divide the g minus 27 to the 2/3 over. Keep the negative here, so I'll put a -1 dt. Okay, be on the lookout for that. If there's no t, then there's no t, but when you take the antiderivative, you'll get a t. All right, so the fun begins. Now we're taking the antiderivative of both sides with respect to its variable. Well, this side's not so bad. Negative t plus c. The c always goes on the x or t side. But on this side, so tempted for students to do natural log. It is not a natural log when it's a power. Oftentimes these problems will be natural log because there won't be a power. But if there's any power, it's not a natural log. It's a reverse power rule. So raise it by adding 1. Since it's a -2/3, we're going to add 1 and get a +1/3. And then pay attention to the inside. Is the g negative? It's not. So you don't need to worry about putting a negative in front. You just need to put a 3 in front so that when you do your chain rule, the 1/3 and the 3 cancel out. So that one's not so bad, but the 2/3 I think threw people off this year. They're so used to seeing natural logs or whole numbers. If it's fractions, no big deal. All right, and then we plug in our initial condition. I think the initial condition did not change. G of 0 is still 91. So 3 times 91 minus 27 to the 1/3 equals, and this is just 0. So if you really wanted to just carry C as this value, you could, but this one's not terrible. 91 minus 27, we already did, is 64. The cubed root of 64, remember, if this is a fractional power, do the bottom first to take the root and then do whatever the top power says to do. So had this been a 2/3, you take the cube root and then square it. But in this case, cube root is 64's cube root is 4, and then that's it. So 3 times 4 is 12. Now we have our C value, so we come back over here. We plug C in, and all we got to do is get G by itself, and it's GG. So divide everything by 3. Do not need to simplify here or get clever. Just don't even split things. I would just divide it all by 3. Cube both sides. To get rid of a cubed root, you cube. to get rid of a cubed, you cube root. So G, I'm just going to cube it here. And then add the 27, and we're done. And we have our particular solution, aka our function for G. That's a great question. I would not do that. Plug C back in. If you find C, it's more obnoxious to carry C the entire time, but I don't know. It's a good point. I think you're allowed to, I think they want to see it without C. But yes, if you sound C, technically you should get full credit. All right, cool. One more AB1. So I think that's what you're going to see. That's a good little, that was 6 FRQs, by the way, guys. And we did it in less than an hour and a half. So that's pretty good because you'll have an hour and a half to do all 6. I could see maybe not a table accumulation this year and a bit more straightforward graphical accumulation this year. So yeah, you don't have to simply, yeah. I think that's what Christian's saying. You could just leave C plus C in your answer, but I would just plug in C. You solved for it, you may as well just put it in there. That's what I would say. All right, last one. This is graphical accumulation. I want to remind you of everything. This is the graph of G. Now, of the graph of F. Do they give a relationship to function of G? Is piecewise linear? Oh, so this is a cool one. So this is G. Find the x-coordinate of each point in function of the graph of F. G is the derivative of the function F. Okay, never mind. This is not as good as the one I wanted to do, but it's okay. I like this problem. But remember, the setup is usually going to be more like this. They're going to say, hey, here's F. And then they're going to do something like this. G of x is equal to the accumulation of 0 to x, f of t dt. This is called starting with an accumulation function. And you definitely need to remember that first step that I have been constantly reminding you of all year. Take the derivative of both sides and write this somewhere. And box it or something. You need to establish this relationship if they don't do this for you. This problem actually already did it for you, which is interesting. But remember to establish this relationship if they don't. You're going to miss that point, which is really sad. And then from here on out, don't ever say it. Say G prime or say F or G or whatever you're referencing. Never say the function or it because there's too many functions in this problem. All right, I like this one because it involves a combination of things. There's geometry because we got to find areas, and then they actually give you the curve equation, which is this thing right here. This is G. So this one's kind of unique. This is from a few years back. So this function right here is G. So you're actually going to have to do antiderivative by hand. I probably won't do that just for the sake of time. But this is a cool problem. So let's find f of 1, or if f of 1 is 3, and this is the graph of G, and G is the derivative of the f, we're going to have to accumulate to do it. We're trying to find f of negative 5. Well, to get f of negative 5, it is initial condition plus accumulation, and I always do it as where you're at and where you're trying to get. And we're accumulating the derivative of f, which is G. You could put f or G here. Don't do that. You could put f or G here. Sorry, you could put f prime or G here. So this is the setup. Now, because this is graphical accumulation, if it's graphical or a table, you need to flip the bounds and make it negative so that you accumulate correctly. And then from here, now we find the area from negative 5 to 1, and we add it up. So negative 5 to 1, it looks like I would probably do it like this. Here's a rectangle, a square, well, with negative 9. Remember, it's negative area. So first of all, f of 1 is 3, minus, from negative 5 to 1, we have this negative 9. We have this triangle, which is 1 times 3, but divided by 2, so negative 3 halves. We have this, which is just 0, and then we have this triangle right here. So triangle here, 0, and this triangle here, which looks like it's just 1, so plus 1. So with that, don't simplify. Leave it just like that, and you're done. Leave it just like that, and you're done. Don't simplify. Then the fun part, evaluate from 1 to 6 of G, and this is the graph of G. So this is the part where I'm not going to do this one by hand, like go through it all. But to do this one, you want the area from 1 to 6. And this is a combination problem. You basically have to do it as 2 parts. The area, do it as from 1 to 3 of G. And add to that from 3 to 6. Why did I split it up? Because one of these you're going to get by geometry. You're going to do your geometry here. And this one, oh no, it's just like that area volume problem we did earlier. You're going to have to find the antiderivative and plug in the bounds and then just don't simplify. I'm not going to do it. We've done enough of these. Yeah. So do this one by hand, do this one by geometry, add them up, don't simplify, you're done. All right, but it's the other ones I really wanted to do because I want to make sure you remember the notation. Please don't miss these problems. Question C, pretty basic. We've done it lots. From -5 to 6, on what upper intervals is the graph of f both increasing and concave up? Well, remember, f is increasing when f prime is positive. And so that's this one. Concave up when f prime is increasing. Those are your relationships. So I'm looking at where is this graph positive and increasing. And that happens from 0 to 1. And that happens from 4 to 6. Okay, some other questions they could ask. The area from -1 to 0 is just 0. Yep, because it's right on the axis. Yep. Some other questions they could ask. Where's the relative maxes and relative mins? Well, that would be the roots and where you flip the sign. So this one's kind of a weird question because of the fact that it's 0 here. But like, look at 4. 4 is a critical point in the function f. Because remember, this is like, g is like f prime in this problem. So g is f prime. So right here at 4, we have a critical point in f. But it's not a max or min because we didn't change sign. You have to change from positive to negative or negative to positive. So in this case, we were looking at, and make sure you write it because they say give a reason. This is the reason. Say f is increasing when f prime is positive and f is concave up when f prime is increasing, and then give the intervals and always, always, always use parentheses, never brackets. Even if it is a bracket situation, which sometimes it is, parentheses will get you the safe bet. All right, and then the last one that I definitely wanted to focus on, D, because it's been a while. We're looking for inflection points of f. And this is the phrase you always write. Inflection points occur where f prime, because we're using the derivative graph, goes from increasing to decreasing or vice versa. That's the phrase. Don't say anything else because you're going to mess it up for stupid reasons. Don't say it's where the critical points are because that's not true. Because you can have a critical point where you don't change from increasing to decreasing and then it's not an inflection point. You have to change concavity in the original, which means you have to change from increasing to decreasing in the derivative. So where does that occur? 4. Nowhere else, right? Because here we didn't change, we went constant to increasing, to constant to increasing, to constant to decreasing. Right here, decreasing to increasing, x equals 4. That's it. Also, never, ever, ever give the y coordinate because it's not the real y coordinate. If you say 4, 0, put a sad face in your 0 because it's not 4, 0. 4, 0 is the point on the derivative graph. It's not 4, 0 on the original function. We don't know what it is in the original function. Well, we could find it, but why? We don't need to do that. Piecewise linear just means it's a bunch of pieces that are all straight lines. They do that so that you can assume these are triangles. If they didn't say linear, you wouldn't be able to assume that these are triangles, and then you'd be in trouble. But you can assume that these are all straight lines. Yeah, piecewise linear. That just means that they're all straight lines. They're piecewise. They're not, and there's a bunch of points of discontent, or a bunch of cusps. Which, last point on this one, remember, if they were to ask you something like find g prime or f double prime at -2, that would be DNE. You could say cusp. The better way to say it is that the left-hand slope does not equal the right-hand slope. So for example, if they wanted you to find f double prime of -2, or show that it does not exist. I would say D and E. I would not say cusp. I would say it's because the limit as x approaches -2 of f prime of x does not equal, from the negative side, sorry, does not equal the limit as x approaches -2 from the positive side. And if the left-hand limit doesn't equal the right-hand limit, that means the limit of the slope doesn't exist, which means the derivative does not exist at that point. Okay, so that gives it 7, or that was 6, sorry, I lied, because that was 6 FRQs. I did not do a grab bag with you, because I think you're going to see a grab bag this year. I just don't want to talk about it. That's on you to figure out. But remember your general derivative rules. Could be implicit differentiation. Could be like a lot of product rules with a table and chain rules and quotient rules and all kinds of stuff. Grab bag just means it doesn't fit this format. So it's not an accumulation. It's not motion. It's not area volume. It's not differential equation. It's some kind of other mix of topics. It's like general derivatives, find where functions increasing or decreasing. Some of the ones in the past would be like, here's 3 different functions, g, h, and f, and one's given by a table, one's given by a graph, and you have to do different things that we've done all year, but it doesn't fit a mold that I can like work you through. Okay, so last one I'm going to do is series, but let me ask the chat, is anyone from BC even in here? I'm not going to do it if there's no BC kids. Okay, cool. Good. Just want to make sure. So I'm going to do the series one just to remind you. This is a series one that I think, good. Oh, lots of you. Awesome. Good. Okay. All right. Bye, everyone else. Yeah, AB, you guys can log off or you can stick around and ask questions. I'll be on for a little bit afterwards if you have questions. But I'm going to do this series one real quick to remind them of how these work. So I like this one. Look, this is a derivative rule series. In other words, you're going to have to build the Taylor series yourself. You can't use a Maclaurin. Although this is a Maclaurin. It just means we're centered at 0. That's how I knew it was a Maclaurin. You're going to have to build it yourself from the formula. So remember the formula. The formula for a Taylor series is, if we're centered at 0, f of 0 plus f prime of 0 times x. I was trying to lag out a little bit. Plus f double prime of 0, x squared over 2 factorial. Plus f triple prime of 0, x cubed over 3 factorial. Now the AP test likes the Maclaurins, the ones where it's like use sine to build one of the more complicated versions of sine, or use e to the x to build a more complicated version of e to the x. They haven't done these in a while, but they used to. So I have a feeling maybe they're going to do another one of these again, where you got to use a derivative rule to generate the function yourself. So this one's also pretty cool because they actually give you the answer in the first one, and they're just making sure you do it correctly. So watch. Show that the first 4 non-zero terms of the Maclaurin for f are this. They're giving you the answer, so they just want to make sure you're doing it correctly. So here we go. Part A. F of 0 is 0. Hooray, that you gave that one. F prime of 0 is 1. They gave you that one. Plus, here's where things get interesting. To find f double prime of 0. In other words, if I plug 1 in here, 1 plus 1 is 2. So to find the second derivative at 0, this says use the first derivative at 0 and multiply it by whatever you're plugging in for n. So we're plugging in 1 for n. So -1 times f prime of 0. So this is actually called recursive. It's using a previous term to get the next term. It's a recursive way of defining something. So the previous term was 1, so we're doing 1 times -1, so this gives me -1 times, oops, that was this one. Sorry, I'm losing my place. -1 x squared over 2 factorial, which is exactly what I wanted. Okay, the next one, to get the third derivative. It says to get the third derivative, now we're plugging in 2 for n. So to do that, it would be negative, so I'll put it right here, I guess. To find the third derivative, it would be -2 times f double prime of 0, which was -1 from the previous part. So that means it's 2. So plus positive 2x cubed over 3 factorial. And then they want me to do one more. And did I get it right so far? Yeah. Remember, 3 factorial is 6. 2 divided by 6 is 3. So last one. Then they say to find the fourth, plug in 3 for all of these. And it'd be -3 times the third derivative, which was 2. So -3 times 2 is -6, so minus 6x to the fourth all over 4 factorial. And by simplifying, you get 1 minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the fourth. And we did it. Oh, you're right. 1x. Good catch. Yes. Yep, good catch. 1x. That was bad. I forgot this little x. I jumped the gun. Yep, so this is better. And I probably would have caught that because it's got to be an x. Good catch. All right, B. Determine whether the Maclaurin series described in part A converges absolutely, converges conditionally, or diverges. Okay, so when they throw these words at me, absolutely, conditionally, or diverges, and they're telling me add x equals 1, the first thing I should do is plug in 1. But the second thing is, that means it's having to do with alternating series. So alternating series is what's going on, and we saw that. Let's plug in 1 and check out what's going on. So 1 minus 1/2 plus 1/3 minus 1/4. And this series should look very familiar to you. It is the alternating harmonic. And the alternating harmonic, you should know whether it converges or diverges. It's alternating. So since it's alternating, you could say something like it's alternating series test. And you could say that it's decreasing and approaching 0. Decreasing in absolute value to 0. Therefore, it converges. However, to determine if it's absolutely or conditionally, you look at the non-alternating version. And the non-alternating version diverges. So in other words, this one converges conditionally. Yes, the AB review is done, but when I end this session, which will be like 10 minutes from now or less, you can go back and watch the video and kind of skip through parts or 2 times speed it or something. It'll be on the VOD. But yeah, the AB review is done. Weren't you here the entire time? The AB review is done. I already said that. I'm only going to do this last series for BC and then I'm done. Cool. All right. So we conditional convergence. Part C. Write the first 4 non-zero terms and the general term for, it wants me to take the antiderivative of this series, which we've done lots. So to take the antiderivative term by term, you'd get 1/2 x squared minus raise the power x cubed. So put a 3 down here, so 1/6 plus x to the fourth and put a 4 down here, so 1 over 20. What am I doing? 1 over 12. 12. Right? Let me make sure I'm not messing up here. 1/2 x squared cubed, put a 1/6, 4, 1/12. Yep. And 5th power, so minus 1 over 20 x to the 5th. Boom. Who are you, by the way? I don't even know who you are. All right, I think that's all I want. So write the first 4 non-zero terms. I want the general term lame. Okay. Well, to do that, just take the antiderivative of, they didn't even have a general term here. That's really obnoxious. All right, so this is a case where I may want to look at how this thing is being built. So plus dot 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 plus. It's alternating. Let's start there. So we need a -1 to the n component. We need a x. The powers look normal, so let's just do that. So x to the n. And it starts with the second power, so that's all good. It's these bottom ones we're going to have to figure out. How do these bottom ones get built? This is a 2. This is a 6. 12, 20. Well, this is where, oh, what's up, Matt? This is where you have to try to be clever about how it was built. And I don't really have a great offer for you on this one because nowhere did you have a general term. You may have to go back and see how the previous general terms were built, but I'm going to show you what's going on in this one. 2 you got by doing 2 times 1. 6 you got by doing 3 times 2. 12 you got from 3 times, or 4 times 3. 5 you got, or 20 you got from 5 times 4. So it's like n times n minus 1, but you're starting by plugging in 2. So it's n, times n minus 1. How would you know to do that? You just got to kind of think of, is it factorials? Well, I knew it wasn't factorials because we don't have anything that's 12. 20 is not one either. If you see 24, that's 4 factorial. If you see 6, that's 3 factorial. But in this case, I kind of just had to think about, okay, what's the pattern going on here? All right, and finally, D. Let Pn 1/2 represent the nth degree Taylor polynomial for G, which I just found. So evaluate x where G is the function defined in part C. Use the alternating series error bound to show that the 4th degree polynomial approximation. So right here, if I plug 1/2 into this, and I don't even have to do it, they didn't even ask me to give the approximation, but if you plug 1/2 in, you're going to get P4 of 1/2. The difference between that and the actual value is off by, at most, the error bound. But wait, before you use the error bound, you need to say you're allowed to use the error bound. So you say something like, since G is an alternating series that decreases in absolute value to 0, use the alternating series error bound. Say that phrase if you see an alternating series error bound. Yeah, that would be partial credit on this past one if you got the general term wrong for sure. So since we're using the error bound just means plug into the next term, which is this term. And remember, it's absolute value, so you don't even have to worry about the negative. It'd be 1 over 20 times 1 over 2 to the 5th, because we're plugged in 1/2. 2 to the 5th is 32. 32 times 20 is bigger than 1 over 500. I don't even need to solve it. That's it. Done. Because you said that I'm allowed to use the alternating series error bound. I found the alternating series error bound, and that value is less than the value you set for me to find, so I've shown it. And that's all you have to do. Make sure if they ask for the actual approximation, this one did not. It did not say give an approximation. Make sure you plugged 1/2 into the polynomial and give it, but this one didn't. It just asked you to confirm that a polynomial approximation would be less than it. All right, other things, make sure you know your tests. If they ever ask you to prove a comparison is good, use the limit comparison test. This one's not an interval of convergence. That was last year. So, but remember interval of convergence, set up the ratio test, all that fun stuff. Other things real quick. Don't forget dy over dx in polar land or parametric land is dy over dt all over dx over dt. Don't forget this formula. That's a big one for polar or parametrics. Don't forget your speed formula for parametrics. Square root of y prime of t squared plus x prime of t squared. If I ask for total distance, remember it's the arc length formula. So from A to B of your speed with respect to t. Polar, remember your formulas, x equals r cosine theta will pop up. Y equals r sine theta will pop up. If you see a polar, don't forget how to plug in r and take the derivative with respect to theta to get dx d theta, dy d theta. Divide those to get dy dx. All right. Newton is busy. I am actually going to go make ice cream, but I can't bring it out. It takes too long to make, but I'm going to go make some. I'll take a picture of it, though, or a small video of it. But I think that's it. It's an hour and a half. My throat's like parched, man. That's good though. That was 7 FRQs. Accumulation, area volume, differential equation, series. All right, so that's pretty much all I'm gonna do. If there's anything you want to go back and watch when I'm done, you can go back and watch it. But it's a lot. It's a lot of stuff to remember. That doesn't even cover the multiple choice stuff. Don't forget like L'Hopital's rule. Show the numerator's limit approaches or equals 0. Show the denominator's limit equals 0. And then do L'Hopital's rule. Limits. Remember, limits exist at holes. They don't exist at jumps. They don't exist at asymptotes. No. I won't do that. You bring me stacks. We can all split up. We'll just go steal them from Mr. Yip. All right, I'm done. Thanks. What a great question. Maybe not. Maybe I'll change your grade. What just happened? What does that sound? All right, we good? Get some sleep now. Don't stay up all night. Sleep, bring your calculators, show up on time, rested, ready to go. Make sure you answer the questions you know how to do. Don't stress the ones you don't know how to do. And that's it. Bye. Bye, bye, bye. Cool. 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 All right, I'm shutting it down. Shutting it down. See you guys tomorrow.